Okay, welcome back. Carrying on with the theme of diffraction then, hopefully you've watched the previous video where we talked about diffraction in general and then looked at single slit diffraction. We're going to think today, or in this video, about something called diffraction gratings. Now on the screen, your screen at the moment, you can see the pattern we had for a single slit. You can then see underneath that the pattern we had for double slit. Now if we carried on adding more and more slits, you can see what is happening on there. We're building up 3, 4, 5, 7 slits. And if we imagine that we keep doing that and we keep building up more and more and more and more slits, what will happen is we basically will end up with a much clearer or sharper interference pattern as we gradually get more and more slits involved. And once we get to a sort of a high enough number of slits, we tend to call it a diffraction grating. So a diffraction grating essentially just consists of lots and lots of closely ruled lines. It's basically lots and lots of slits in a row. Now we're talking sort of 300 lines per millimetre, for example. So very, very close. Now, if you look at a diffraction grating, that's a diffraction grating. You can see through it. The lines are so close together, you can't really, well, you can't make them out at all. But they are there, okay? Lots and lots of slits all in a row. Now, what that means is we'll still see an interference pattern. Imagine there's our diffraction grating. Okay, and I shine light at it. Now again, I'm going to assume monochromatic light because that makes it a lot easier. So here's my light, possibly a laser, shining at the diffraction grating. Now what I will see is I will see a load of maxima, just like we did before. If I had a screen over here, I would see maxima. And they have certain names now. And so there will be a maximum straight ahead. Okay, and that is called the zero order maximum, sorry. Okay, zero order. Then if we change the angle and look out here, we'll find then eventually there'll be another maximum, and that would be called a first order maximum, or in other words, n equals 1. Then a bit further out here, we'd have another maximum. That would be our second order maximum, or n equals 2, and so on. Then also, both sides are going to have the first, second, and third order, and so on, however many are actually visible in that particular case. Okay, let's look then in a bit more detail at why we get this pattern and think about deriving a formula. Now, it is quite difficult to visualize what is going on in a diffraction grating, and unfortunately even the diagrams which are supposed to help sometimes make it a bit more complicated. So I'm going to show you a diagram now, don't panic. Okay, now let's see if we can make sense of this diagram. On the left you can see the waves coming in, and P, Q and R and so on, those are the actual, they're the gaps in the grating, they're the slits. Now, all of the semicircular lines on the right hand side, those are the waves passing through, they're the wave fronts as the wave spreads out from every single one of those slits. And if we imagine that we're looking towards the grating from the right hand side, we know that we will get constructive interference if the path difference between one source and another is an integer number of wavelengths. So imagine looking along this direction that's labelled direction of first order wavefronts. Imagine looking this way. Well actually, if we look, okay, the path difference between the light coming from P and Q is one wavelength. The path difference between the light coming through P and R is 2 wavelengths. And if you look at any point along here, the difference between P and R is always 2 wavelengths. The difference between P and what I suppose you'd call S is 3 wavelengths. So between any two slits here, the path difference between the light coming through those slits is an integer number of wavelengths. And so therefore you will see a maximum. Now let's look at kind of deriving the formula. Okay, now this derivation is one which you need to be able to do. You need to be able to reproduce this in the exam and explain what you're doing. So what we're going to do, we're going to simplify that diagram down massively. Okay, so let's just consider we're going to consider 3 slits like that. That's 3 slits on our grating. Okay, and we're going to say that we've got our distance between the slits is d, small d. And we're going to look at the directions where we get a maximum. So we've got light arriving this way. And we're going to consider for this, we're going to think about the first order maximum. So the first order, and think about the first order wavefronts. And so we'll do it down just because it might be easier for me to draw. Okay, now, good news, there are no approximations in this derivation, not like the one we had for the double slits. And the reason for that is you may have noticed I've been talking a bit about angles. Actually, because we're no longer assuming small angles, we're not talking about the physical distance between them. If you put a screen here, we're not thinking about how far apart the maxima are. We're actually looking at, well, what angle do they occur at? What angle would you have to look at the grating at to see a maximum? And so if we just imagine we had a line straight across there, our first order angle is there. Okay, that's the angle between kind of the line going straight perpendicular to the grating and my first order maximum. Okay, now this is where we have to think a bit about what we said earlier about the idea of path difference. For our first order maximum here, okay, if I just draw a line along there, so that's a right angle. That is the path difference. Okay, that blue line there, that's the path difference between the light coming through this slit and this slit. So for the first order maximum, that's lambda. That's one wavelength. And actually, if we use a little bit of trigonometry or geometry more, that's theta. That means this angle in here is 90 minus theta, which actually means that our angle here in the triangle is theta. Okay, I apologise that it's quite small, but that is theta in there. So, if we just look at this triangle here and apply trigonometry, sine theta equals opposite, which is lambda, over hypotenuse, which is d. So we've got sine theta equals lambda over d. Or we could say that lambda equals d times sine theta. Okay, and that is for the first order. That's for the first maximum. But if we now imagine extending that to a general case, okay, if we extended this to a higher order, the condition that we would have for a maximum would be that this path difference here was an integer number of wavelengths. So instead of having lambda over d, we would have n lambda over d, n times lambda, integer times lambda. So if we generalise this, n lambda equals d sine theta. And n corresponds to the order number. So for first order, n equals 1. For second order, n equals 2, and so on. Okay, going back to our original diagram, okay, 0th order, obviously n equals 0, because the angle's always 0. But going up, however many orders you've got, n lambda equals d sine theta. Okay, so from our formula then, we can conclude a couple of things. So let's just think about how we could, or what would cause the angle between the maxima to increase. So angle between the maxima increases if, well, from there, a couple of things that you could do, well, two things really you could change. Either if lambda increases, so in other words, higher wavelength, or if d decreases, in other words, you have a smaller separation between the slits. Right, let's test the theory then for our diffraction grating. So I put the diffraction grating in the holder, so when I turn the laser on, we are expecting to see a number of bright fringes, but we would expect them to be a lot more spread out than we saw for the double slit, because essentially we're looking here at angles, and there you go. Okay, I've switched it on, and you can see there we can see a few. We can just about see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So probably from the central, I'm going to guess that's the central one. So that's 0th order. We then got first order, second, third, and fourth. First, second, third, fourth. On this side, you can just about see a few more. Okay, so there we have it, our pattern for diffraction grating. Now, we would expect to see if I change the wavelength. If I change the wavelength, we would expect to see different angles. So let's try with the green. There's the green, and in fact there are a lot more orders visible there. So they're both on at the same time. Right, you can see that the green have got their, I think that's the 0th order. The green have got more orders visible because the angles for each order are smaller. Okay, but hopefully that gives you an idea of actually what it would look like in reality. Now again, I can change to, so that one at the moment is 80 lines per millimetre. I can actually change to one with a much closer together ruling. So this is 300 lines per millimetre. Let's see what the difference is. Well, the difference there is I get a lot fewer orders visible. The angles are a lot bigger. And that makes sense. That agrees with our formula because if D, in this case, it's a lot smaller, that means our angles become a lot bigger. Okay, just a few little notes then. Things to be careful of, things that pop up in questions. Firstly, D is the distance between adjacent slits on your diffraction grating. Sometimes, though, they will try to sort of confuse you a bit by, instead of giving you D, they give you a number of slits per metre. So, or number of slits per millimetre. So just in terms of converting that, so number of slits per metre, or N, capital N, is 1 over D, if D is in metres. That shouldn't really be a surprise to you. To find out the number of slits per metre, you do 1 divided by the distance between two adjacent slits. Just as a quick example then, here 300 lines per millimetre. If we wanted to work out D, so D equals 1 over N. N is the number per metre. Now, 300 lines per millimetre is going to be 300 times 10 to the power of 3 lines per metre, because there are 1,000 millimetres in a metre. So our distance between slits is 1 over 300 times 10 to the power of 3. So you do have to be careful there, and you will get a really, really small number. In fact, in this case, that gives you an answer of 3.3 times 10 to the minus 6 metres, or 3.3 micrometers or micrometers. Right. A common question also is, it will say, what is the maximum order you could see, or how many maxima would be visible? So to do that, all you would need to do is put theta equals 90 into your equation, because that would be the maximum possible order that could be viewed. So you put theta equals 90 degrees into your equation. Now theta is 90, that makes sine theta 1. Okay, so n would then be d over lambda. But do be careful. Let's say you got an answer of 4.3. Just, I've made that number up, but let's say your answer was 4.3. You'd have to remember to round down, because that would mean you could see the 4th order, but you couldn't yet see the 5th order. So the maximum order would be n equals 4.